Good afternoon, everyone. I am Micaela, and today I will be presenting our work titled Revisiting Point Cloud Classification, a new benchmark dataset and classification model on real-world data. In the recent years, deep learning techniques for point cloud data have demonstrated great potentials in solving classical problems in 3D computer vision. This was pioneered by PointNet in 2017, and multiple works followed then after. Among such problems is object classification, and several recent methods have reported very high accuracies on CAD model datasets such as ModelNet 4D. The current progress on classification has also witnessed a trend of performance saturation, and this leads us to the question, is the problem close to being solved? Despite performing well on synthetic CAD data, we argue that point cloud classification is still an open problem and is far from perfection, especially when working with scans. Differences between CAD and scans are caused by object clutter, occlusion, brokenness, and background, etc., making the low-level geometry very different and learning more difficult. In order to show this, we introduce a new benchmark dataset for point cloud classification based on real-world data. We leverage on existing indoor scene datasets, ScanNN and ScanNet, to introduce ScanObjectNN, a new object dataset from real-world scans for point cloud classification. ScanObjectNN contains 15 common categories with 2,902 unique object instances. Our raw data is represented by a list of points with coordinates, normals, color attributes, and semantic and instance labels. Additionally, to further enrich our data, we introduce different object perturbations by perturbing the original bounding box. This is to introduce variations in background, object clutter, and partiality. All in all, our dataset has a total of around 15,000 objects with 6 different variants and 5 train and test splits. We also support part annotation for real-world scans. Our experiments show that even if point cloud classification performs well on CAD models, it is still a challenging problem when dealing with scans and achieves significantly lower accuracies. We conducted a comprehensive bench evaluation on existing point cloud classification methods on our dataset. That includes detailed comparisons of these methods. To discuss in more detail, object perturbations were done by randomly translating, rotating, and scaling the axis-aligned bounding boxes of the objects. From our experiments, we found that translation augmentation causes the strongest performance drop. Our benchmark also helped us recognize 3 open problems that are present when dealing with scan data. First, how to handle object partiality. For example, when scans are incomplete or where objects are occluded. Second, how to handle background points present when scanning the object. And third, how to generalize between CAD and scans. For example, training in one domain and testing on the other. We introduce a simple background-aware or BGA model to handle the problem on dealing with background. The idea is to classify only based on object points and not on the background. Hence, we have a classification and a segmentation branch, where the segmentation branch is conditioned on the learned intermediate class vector. We introduced BGA PN++ and BGA DGCNN that were based on 2 recent state-of-the-art methods. Results show that our BGA models achieve the best results on our scan dataset, and we have an online leaderboard, so please check that out. From our experiments, we also observed that DGCNN-based networks generalize better across the 2 data domains. That is, it has the highest performance when trained on synthetic data and tested on real, and vice versa. In summary, we introduced ScanObjectNN, a new point cloud dataset on real-world scans that includes perturbation variants of varied difficulties. We also introduced BGA models as an initial solution to this problem. Thank you.